Hi there, welcome back. Today we're going to talk about the square root function. Now the square root is complicated enough when we take the square root of the -1 and we get I or minus I maybe. But what we're going to do now is we're going to talk about the square root function generally as it takes any arbitrary complex number input. Can we take the square root of I? What would that be equal to? Can we take the square root of any arbitrary complex number? How would that work? Where this is coming on the after the end of the theorem about derivatives of inverse functions. Square root is clearly going to be the inverse function of the squaring function. And so we can use the theorem about the derivatives of inverse functions to assess what is the derivative of the square root function. But we can't do that until we define the square root function. And there are some basic questions about how you would do that. So what we're going to do first is we're going to just approach this very gently. How would you define and recognize the square root function on the complex plane? And then once we have an idea what that would be, then we'll use what we know about inverse functions, try to show that it is an inverse function for the squaring function, and then we'll try to calculate its derivative. So let's get started. So the first thing we want to do is we want to think about the squaring function because that's the function that we're trying to invert. So the square function, it of course has the formula f of z equals z squared, but it's very hard to just solve for, if you have w equals z squared, it's very hard to just solve for z in terms of a and b. And so what we're going to do is we're going to think about this squaring function in terms of the polar coordinates for the function z. So if z is going to be r times cis theta, so why do I call that polar coordinates? Because this is expressing z in terms of its distance from the origin and its angle theta. So if we have a point in the complex plane, then this could be, then this would be the value of theta, and this would be the value of r, and this would be, this length here will be r cos theta, and this length here will be r sine theta. And so this point in the complex plane will be r cos theta plus I r sine theta, which is r cos theta plus I sine theta. And that's the definition of cis theta. So that's r cis theta. So when we write an arbitrary complex number in the form r cis theta, then we are implicitly really thinking in polar coordinates here. Now, if that's the polar coordinates for z, then what are the polar coordinates for z squared? Well, z squared is going to be r squared times, not cosine, but cis theta quantity squared. And as we've seen, cis theta squared is cis 2 theta. And this is consistent with our geometric interpretation of complex multiplication. As we've seen, if you multiply two complex numbers, the moduli of those numbers multiply to yield the modulus of the result. And the angles of those complex numbers, the thetas, they add to give you the angle of the result. And so here, the theta is getting added to itself to yield 2 theta, but the r is getting multiplied by itself to give you the r squared. So using this notion of, well, I'm trying to square the modulus here and I'm trying to double the angle, then we can start to get an understanding for what it would mean to take the square root. So we could define the square root to be, well, we would just do the reverse. So square root of z would be the square root of r. Now, is this a circular definition? We'll come back to it. So the square root of r times the cis of theta over 2. So I've just defined the square root of z in terms of the square root of r, and you have to question, did I or didn't I give you a circular definition? R is necessarily a non-negative real number here because it's the modulus of z. And so I'm taking for granted that we already have a square root function defined, but applying to the positive real numbers. And so this is the square root of a positive real number in the ordinary sense, and this is the new and invented square root of the complex number in the new sense that we're writing. So here I'm taking the angle and I'm dividing it by 2, and then I'm taking cis of that. So let's try to indicate how we would do this geometrically on the complex plane. So let's just do a few examples, starting with the square root of 4i. So, so example here, we're going to calculate the square root of 4i. So let's let z be 4i. Then the modulus of z, which is r, is going to be 4. And the angle here, well, I actually have some choices, but there's an obvious choice here. The angle here is the 90-degree angle, which is pi over 2. So theta is going to be pi over 2 when you're dealing with the complex number 4i. So theta is going to be pi over 2. Now, why did I say there are some choices? Well, I could have taken, you know, the same plus 2 pi or the same minus 2 pi, and we could worry about what happens when I do that. But pi over 2 is the natural thing to take. So then the square root of z will be the square root of 4, which is 2, times cis of pi, not pi over 2, but pi over 4. So cis of pi over 4 is the angle pi over 4, which is a 45-degree angle, and we go out 2 units there. And so this is actually turns out to be the point root 2 comma, not comma, root 2 plus I root 2 would be this point here. So that's going to be the square root of the point 4i. And what I'd encourage you to do is maybe pause the video, multiply this complex number by itself, and you can verify that you really do get 4i. So that's how we calculate the square root of a complex number. The only thing, so calculating the square root of the modulus is really pretty easy. The only thing that we should really worry about is actually dividing the angle by 2. The reason we should worry about this is because angles are not always well defined, and there seems to be some debate about what is the right version of the angle. So I want you to remember here that in the complex plane, the negative real numbers here have an angle of pi, positive pi. And the numbers that are slightly more negative in the imaginary sense, the numbers here have an angle which is slightly more than pi. That is, if we're using a range of angles between 0 and 2 pi, they do. But if we're using a range of angles between minus pi and pi, then they don't. Then they have an angle closer to minus pi. So this angle might be the negative angle here. So the angle could be approximately -3, like slightly less than minus pi. So now it doesn't seem to matter whether we take an angle to be slightly more than 2 pi or, slightly more than pi versus, you know, just barely almost negative pi. It doesn't seem to make much difference because we get the same point. But by the time we take that angle and divide it by 2, then it will have made a difference, right? If we have an angle which is slightly more than pi and divide it by 2, it will be here. But if we have an angle which is slightly shy of minus pi and divide it by 2, then it will be slightly shy of this value and it will be here. And you can tell here that these are opposite angles. And so which angle we choose to represent the thing doesn't make a difference when it comes to actually calculating cis of that angle, but it might make a difference after that angle gets divided by 2. So this brings us to the argument function. So given z in the complex plane, so we write argz for the angle of z with an understanding that the argument has to lie in a certain range. So the argument of z has to lie in the range from 0 to 2 pi. But this is not, so this is basically the angle as a function of z, but this is not the only option for how to write that angle. So I want to introduce immediately another one, which I'm going to call arg1 of z, or arg1 of z, um, with the understanding that arg1 of z would be between, it would be the other natural choice between minus pi and pi. Now, these aren't the only two choices, but they are the two natural choices for defining the range of angles that are possible for a complex number. So I'm intentionally introducing a little bit of ambiguity here, right? You could have the argument function that would look one way, or you could have the argument function that would look another way. And it doesn't matter when you figure out which complex number it is, but it will matter when you take half of it, when you take half of this argument, right? When you take half of these numbers, you will always get numbers between 0 and pi. When you take half of these numbers, you will always get numbers between minus pi over 2 and pi over 2. And those are like essentially different ranges. And so which one of these you're using to really specify the angle of these things is going to affect the definition or our interpretation of the square root. So let's say more precisely, the square root is going to be the square root of z is going to be the square root of the modulus of z times cis of the argument of z divided by 2. So here, this is the same formula as this, but I'm just showcasing how everything here is actually a function of z, right? Z is, I mean, we've got a lot of letters cluttering this up, so it looks like it's a function of many things. Everything is ultimately dependent upon z. R is the modulus of z, written this way, and theta is the argument of z, written this way. And now this indicates how if you swap out this argument function and swap in a different argument function, you get another function which would sort of serve as an alternate square root. And that's both good and bad. There are uses for this, but it creates an ambiguity which is confusing. So if we don't say, I mean, if we don't say anything more specific, this will be the definition of the square root function. We will define it to be this, and this argument means that the angle has to be between 0 and 2 pi. Now, let's see what this means geometrically about, well, first, before we do this, let's see that this really is an inverse function for the squaring function, right? So notice, so this marker's going bad. So I guess I'll switch to this one. So notice, yeah, that one's not gonna work. We'll keep trying. So if you take the square root of z and you square it, then what do you get? You get the square root of the modulus of z squared times cis squared of the argument of z over 2. Now, this is a square root of a real non-negative real number and then squared. So those cancel by normal real number properties. And this gives you this gives you the modulus of z. And then here I have cis squared of something. Now, cis squared of something is cis of 2 times that thing by the properties of cis. So this is cis of 2 times the argument of z divided by 2. And then the 2's cancel, and we end up with modulus z cis arg z. And cis arg z is cis of the exact angle that makes z, and this is the modulus of z, and so that gives us z. And this is true for all z in the complex plane. And so we've just shown that the square root function is an inverse to the square function. Well, let's be careful. We haven't exactly shown that it's an inverse, but we've done close. We've shown that the square root function is a right inverse for the squaring function. If we first perform the square root and then perform the square, then we get back where we started. We haven't shown that it's a left inverse, and in fact, it's not. So let's look at its geometry, and it will become obvious that it's not a left inverse. In other words, when you square something and then take the square root, you don't get the same thing. It might sound surprising, but it shouldn't surprise you because that's not even true for real numbers, right? If you square something and then take the square root, sometimes you get a different thing. So it shouldn't bother you too much that they don't work in the other direction. Okay, so the geometry of it, I'm going to try to represent now. So we have This is the complex plane, and all the z's are here. Now, the square root of 0 is 0, so 0 is a fixed point of the square root map. I'm going to try to indicate where the points go. 1 is also a fixed point. The square root of 1 is 1. The square root of minus 1 here is, well, let me represent that the same distance away from the origin. The square root of minus 1 is actually I, which, you know, if you've been paying attention in complex analysis class, is not supposed to surprise you, right? And notice here that that is consistent with this, right? The modulus of minus 1 is 1, and the argument there is going to be pi. So we're going to divide the pi by 2 and end up with an argument of pi over 2, and that'll give us I. The square root of negative I is a little bit interesting. So this point is actually 3/2 pi, and it maps to 3/4 pi. So it goes around here and goes there. And then there are points right about here which have an argument which is almost 2 pi. And when we divide that by 2, we get almost pi, and they move around like this and end up right about there. Now, notice here that you can tell already if this is almost 2 pi and maps way over here, and if this is 0 and maps to right there, right, that's the point, the argument of this point is 0 because that's the value 1 in the complex plane, then this point and this point are close, but they are not mapped to close points by the square root function. This one is mapped way over here. And as you approach in here, you're just getting closer and closer to mapping over here. So what we have here is evidence of a discontinuity in the square root function, right? As we approach from below here, then we're actually getting values over there. But if we approach from above, we're getting values right here. So that's interesting. The square root function is discontinuous. Now, you can start to see what's happening to the angles here. The angles are getting cut in half, but the large angles close to 2 pi are getting shifted over here and becoming close to pi. So the right way to visualize this is it's as if there's a tear that begins here at the origin and stretches outwards along the real axis. The entire complex plane, it tears and separates. And then, like a folding fan, it just wraps halfway back around, right? It just tears here and then closes in on itself. And all of the angles kind of contract until the square root function lifts all the points up here into the upper half plane. So these points all sort of rotate around here, and like a folding fan, it closes up and all the points move to the upper half plane. So geometrically, it's like you took a folding fan and just kind of halfway closed it so that all the points move to the upper half plane. That's part of the geometry. That's the angular geometry of what's happening with the square root function. There's a little bit more going on because the moduli are changing too, right? The points that are far from the origin are moving much farther, and the points that are on the unit circle are staying on the unit circle, and the points that are close to the origin are moving much closer. So there's this kind of weird kind of spreading out phenomenon too. Both of those things are happening at the same time with the square root function. But the important thing you need to notice is that it is not continuous everywhere. It is continuous, well, if we look at this formula, the modulus function is continuous. The square root function is continuous where defined here on the positive reals. The cis function is a continuous function of its real argument. And so the only source of discontinuity for the square root is the discontinuity in the argument function. But the argument function is not continuous, right? It starts 0 and then pi over 2 and then pi and then 3/2 pi and then almost 2 pi and then whoops, back to 0. So the argument function is discontinuous on the positive real axis. And so therefore the square root function is also discontinuous along this positive real axis. So the square root function is discontinuous exactly where the argument function is discontinuous. So who cares? Well, therefore, that is along the positive real axis. And that's a big bummer because that means that it's not continuous there. But if you are absolutely in love with a positive real axis and it just pains you that the square root function is discontinuous along the positive real axis and you just rather it not be so, there is actually a way around this. And that's because there's more than one alternative for the argument function. If instead of using this argument function, which itself is discontinuous on the positive real axis, we use this argument function, which is discontinuous on the negative real axis, then we would just stick a 1 here, and we would get a new square root function, and that one would be discontinuous where that argument function is discontinuous. And it would have a completely different geometry. It would tear along the real axis, and then it would fold out like this, halfway forward, and then we would basically take all these values, open them up, and it would have an image which was the right half plane instead of the upper half plane. So if you're absolutely in love with the positive real axis, you can repair the square root function so that it's discontinuous somewhere else, not where you're in love with those numbers. But there's no way to define the square root function so that it's continuous everywhere, and that's kind of interesting. Moreover, we have to be very, very careful when differentiating the square root function. The square root function is the inverse, more or less, of the square function. When I say more or less, I mean it's the right inverse. It's the right inverse of the square function. And so we can use the formula for the derivative of it. But if the square root is playing the role of the function g in that theorem, and because it's playing the role of the function g, then we can only calculate its derivative by means of that theorem if we already know that it is continuous. And it isn't continuous everywhere. So when we calculate the derivative of the square root function, we have to exclude the points where we already know that that square root function is discontinuous. Now, how do we, let's briefly calculate that derivative, and we'll see that it's just exactly what we would expect. So briefly, so f of z is going to be z squared, and g of z is going to be square root of z, which is defined for all complex numbers, but not continuous for all complex numbers. And then f of g of z equals z. That's true. And so, and now f is differentiable everywhere. And so we don't need to worry about the definedness of f prime. And so, so what do we know? We can conclude wherever g is continuous, then we get the derivative, g prime of z, is going to be 1 over f prime of g of z. And let's calculate what that is. And I actually have one more proviso here, provided f prime is not 0. So, so let's calculate what that is. The derivative f prime is simply 2z. So that's 1 over 2 evaluated at the square root. Now, that's provided f prime is not 0. Is f prime ever 0? Yes, it is 0 when z is 0. So we have to exclude the possibility that z is 0. So let me simply say except when z equals 0, which of course that couldn't possibly be true when z is 0 because it itself would have a 0 in the denominator. So this is correctly the formula for the derivative of the square root function, except when z is 0, but you wouldn't expect it to be true then anyway. So we've used the formula for the inverse function. This is true when z is 0, but it's, sorry, this is true except when z is 0, but notice wherever g is continuous. That is a huge set of exceptions besides g equals 0. And so we should also say here that this is false. So note here, this is false when z is positive real. And that is a bit strange and surprising because there's, I mean, making exception for z equals 0 is obvious because this formula can't even be defined when z equals 0. Making exception when z is a positive real number is very surprising because it's an exception that excludes all of the derivatives of the square root function that we already thought we knew about from normal calculus, right? Because I mean, the positive reals are where it's at when you're dealing with the square root function in ordinary calculus, but we've just excluded those. This function is not differentiable on the positive real line, and that's pretty disappointing. The formula is defined, obviously. If z is a positive real, 1 over 2 root z, that is a defined thing, but g is not even continuous at those points, and so it certainly can't be differentiable at those points. So we get some weird exceptions from the complex plane that we didn't have in the case of the real calculus, and that's a little bit surprising. All right, this is a story of an inverse created by means of the argument function and its derivative calculated by means of the formula for the derivative of an inverse function. And this whole story gets repeated once more in the course when we introduce the logarithm function. The logarithm is going to be introduced as the inverse of course, the important function, the exponential function. And when we do that, we'll be interested in, first of all, is it continuous? And we'll see it has similar problems to the square root function. And then second of all, what is its derivative, which we can calculate wherever it's continuous by means of that same theorem. So we'll see the whole story once more a little bit later in the course.